In Chapter 11, we are going to take a look at the physical property of gases. And gases occur in our everyday life mostly because our atmosphere is made up of a mixture of gas, which we call air. It's about 80% nitrogen and 20% oxygen and small amounts of other gases. And because of this, we're familiar with many of the physical properties of gases. For example, we know that gases expand to completely fill their container, whether it's a tire or a balloon or our lungs. We know that they also take the shape of their container. Now, in chemistry, when we're talking about gases, we will always be talking about gases in a particular container. Gases also have very low density, much less than a solid or a liquid. They are also compressible. Mixtures of gases are always homogeneous, also known as a solution, and they are fluid, meaning that gases flow. So we're going to look at the properties of gases at the molecular level, and that's going to help explain these properties that we see at the macroscopic level. All gases are composed of particles, and when we say particles, we mean molecules or atoms that are moving extremely quickly in the container. Some of them are moving faster than the speed of sound. They move in straight lines until they encounter either the container wall or another particle, then they bounce off. And gases are mostly empty space. Let's take a look at the theory that chemists use to describe the behavior of gases. It's known as the kinetic molecular theory, and particles of gases, either the atoms or molecules, are constantly moving. The attraction between these gas molecules or atoms is negligible, and what this means is that when moving particles hit another particle or the container wall, they don't stick to one another, but they bounce off and continue moving in another direction like billiard balls. And so to maybe put this in perspective, the molecules that exist in solids or liquids are stuck together. That's what makes them a liquid or a solid. And in a gas, these molecules are not stuck to one another. Another part of the kinetic molecular theory is that there is a lot of empty space between the molecules in a gas. Compared when you look at the size of the molecules, it's negligible compared to the total space of a container. And the average kinetic energy, remember kinetic energy is energy of movement, of the gas molecules is directly proportional to the Kelvin temperature. So as you raise the temperature of the gas, the average speed of the molecules increases. Now only it's an average. Not all the particles are moving at the same speed. For example, when one molecule bumps into another, its speed may change, and the molecule that it bumped into will change as well. So it's an average speed that we're talking about. So here we have it, kinetic molecular theory. We have gases that are always, these molecules are always in constant motion. There are no attraction or repulsions between the particles. The collisions are like billiard ball collisions. There is a lot of empty space between the molecules compared to the molecules themselves. And the speed of the particles increases with increasing temperature. And this, of course, we know is an average speed, is directly proportional to the Kelvin temperature. Now, one physical property that's very important to gases is pressure. And this is a physical property we have not addressed yet in this class, so let's take a look at it. We know that gas molecules are constantly in motion, and we also care about gas particles in a container. As these gas molecules move and strike a surface, they push on that surface. And a push is a force. This force is what causes pressure. The definition of pressure is force per unit area. So a gas that has high pressure is hitting the surface of the container with a lot of force. And you can do that by having a lot of molecules hit it or molecules hit it at a very high velocity. Whenever there is a pressure difference, a gas will flow from an area of high pressure to low pressure, and this is what causes winds. The bigger the difference in pressure, the stronger the flow of gas. And if there's something in the gas's path, the gas will try to push it along as the gas flows. And so we definitely see this result whenever the wind blows. So let's take a look at this problem. Two balloons are connected with a long pipe. One of the balloons is plunged down into the water. Which way will the air flow? Well, to answer this, we need to know which balloon is going to have the higher pressure, because pressure is going to flow from high to low. Water is much more dense than air is, and because of this, many more water molecules are going to be pressing down upon this balloon than they would up here in the atmosphere. Therefore, this balloon is going to have much more pressure on it, and the air is going to flow from the high pressure to the low pressure. In nature in general, flow always goes from high to low, high temperature to low temperature, high concentration to low concentration, and here we have high pressure to low pressure. So would a person be able to snorkel at a depth of 20 meters below the surface of the sea? Well, remember, a meter is about a yard, so about 60 feet under the water. Well, that would depend on two things. It would depend on what is the pressure at 20 meters, and is our body capable of overcoming that pressure? Because air or any gas wants to flow from high to low pressure. So if we're looking here, down here is going to be a very high pressure compared to the atmosphere. And any gas is going to want to flow this way, from high pressure to low pressure. So the question is, what is this pressure at 20 meters, and does our body have enough force to overcome the pressure to suck the air back down? So to answer that question, at 20 meters, the total pressure is 3 atmospheres. We'll look at pressure units in just a little bit, but at the surface of the water, the pressure is about 1 atmosphere. So 60 feet down, the pressure is 3 times greater than what it is at the surface. And our lungs can generate enough force to overcome about 1.06 atm. So, to look back at our question, is this possible? No. The pressure is going to be 3 atmospheres. We can overcome a pressure of 1.06 atmospheres. We would not be able to scuba dive 60 feet under, or snorkel. We would not be able to snorkel 60 feet under the water. We couldn't even scuba dive if our tank had a pressure of only 1 atm and we went down 60 feet. Scuba divers have very special tanks that regulate the air pressure. So the air pressure in the tank is the same pressure as the water surrounding you. So therefore, you don't have to overcome any pressure differential. This allows you to take in air even when the outside pressure is large. So when you go down to a depth of 60 feet and the outside pressure is 3 atmospheres, the pressure in your tank is also 3 atmospheres, and that allows your lungs to pull in the air that it needs. Let's look at another example of how gas pressure comes into our everyday life. If you have a straw in a glass that has a drink in it, the level of drink is going to be exactly the same inside the straw and outside the straw. There is pressure on this liquid coming from the outside air. If you suck the air out of the straw, then what happens is the pressure inside the straw gets lowered, and the outside pressure, due to the atmosphere, is larger. The atmospheric pressure is going to push down on this liquid and push it up the straw. If you were to stop sucking the air up, and then let go, then the air would refill into the straw and the pressure inside the straw up here would be the same as the atmospheric pressure, and the levels would be the same. But as soon as you decrease the pressure by sucking on the straw, then the atmospheric pressure pushes down on the liquid and pushes it up the straw.